This video is about the first derivative test, so let's dive in. Let f be a differentiable function on an open interval. If the first derivative is positive, then we say f is increasing, and if the first derivative is negative, we say f is decreasing. Let's just go ahead and look at a graph and sort of make sense of that. So a graph is increasing, right? That means the y value should be getting bigger, right? So like for example, if I look at this graph in blue, the y values are going up, 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 up. They're increasing and then they stop, right? So here at x1, there's a sort of change here. And then they start decreasing, 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 and then they sort of flatten out again, and there's a change at x2, and then they start increasing again. So if you think about the slopes of tangent lines, remember the first derivative represents slopes of tangent lines. So if I think about these, right, all these tangent lines are going to have positive slope, right? So first derivative is positive. That's sort of indicating that I'm increasing. Whereas over here, right here, the slopes of tangent lines all have negative slope, which sort of indicates that my function is decreasing. Now, you might notice that I'm switching increasing, decreasing, decreasing, increasing around special places in the graph, right? The sort of tops of hills and the bottoms of valleys. Those have a special name, which are called critical numbers. So critical numbers are where the first derivative is equal to 0 or undefined. And of course, if you want the first derivative to change from positive to negative, it's got to cross through 0, right? So like if you're switching from increasing to decreasing or from decreasing to increasing, then you either have to have a break, right, like a discontinuity, so the first derivative wouldn't exist, or you have to have the first derivative being 0, right, a place where it sort of switches from going up to going down or from going down to going up. So the first derivative test is trying to sort of algebraically tell us whether when we change, we are dealing with a maximum or a minimum. So you can see in this, just because we've got the graph in front of us, that this is a local max, right? This critical number should go with a local maximum, and this critical number should go with a local minimum. Okay, and the first derivative test is an algebraic way of examining whether a critical number goes with a maximum or a minimum without having to look at the graph. Okay, so let's check it out. The first derivative test for critical numbers. Assume that f is differentiable and let c be a critical number. So remember, that's where the first derivative is 0 or undefined. Then, if f prime of x changes from positive to negative at the critical number, then the y value is a local which? Max or min, right? And then if it switches from negative to positive, what's it going to be? So you might pause the video here and see if you can fill this in. So go ahead and pause and try it out. Okay, if you're back, if the first derivative is changing from positive to negative, that means the graph was increasing and then it started decreasing. That's going to create a local maximum. Right? And similarly, if my first derivative was negative, that means my graph is decreasing, and then first derivative becomes positive, so my graph starts increasing. That's going to be a local minimum. So again, the first derivative test for critical numbers is trying to tell you algebraically whether or not a critical number goes with a maximum or a minimum. Okay. Quick question. What happens if the first derivative doesn't change sign? So is it even possible that you have a critical number, but the first derivative was positive on one side and then is positive again on the other? In short, yes, that is possible. And again, you may want to pause the video and try and answer this yourself. But the answer is that it's neither a max nor a min. Specifically, the y value that goes with your critical number. For example, the one that I always sort of use is x cubed. Right? So if I'm thinking about x cubed, it looks approximately like this. And it's hard to tell from looking at the graph, but there is actually a horizontal tangent line right here at the origin. So 0 is a critical number for this graph, right? If I take the derivative, I get 3x squared, and if I set that equal to 0, 0 is a solution to this. But the graph is increasing the whole way, right? I mean, like, it's positive on this side, and it's positive again on the other side. So if you don't get a sign change, then it doesn't go with a max or a min, as is the case here, right? This is nothing special. It's just sort of sitting in the middle of the graph. Okay, so let's consider a function, and I'm just going to go polynomial, something simple, so I can sort of exemplify the concept. We want to analyze the critical numbers. When you see that language, that usually means determine if the critical numbers go with maxes, mins, or neither. So to start this problem, we need the critical numbers. Critical numbers are a first derivative thing, right? So we take the first derivative, power rule, so 3x squared minus 27. Is the first derivative ever undefined? No, not in this case because it's a polynomial. So instead what we're going to do is take it and set it equal to 0, because remember critical numbers are where the first derivative is 0 or undefined. Then to solve this, right, I'll move my 27. X squared is 9. So x then is going to be positive or negative 3. So x equals 3. X equals negative 3. These are my critical numbers. Okay, so far so good. So now what I want to do is test these critical numbers and see whether or not they go with maximums and minimums. And in particular, I don't want to have to know what the graph of f looks like to be able to do this. So essentially what I'm going to do is take these critical numbers and put them on a number line. And I'll talk about why that is in just a second. So I'm going to put these sort of in order on the number line. Right, so 3 over here, or negative 3 over here, and 3 over here. And what this does is divide the number line into intervals where the first derivative behaves similarly. So specifically, the intervals are negative infinity to negative 3. That's the sort of left arm. This middle arm, or this middle segment, negative 3 to positive 3. And then on the far right, 3 to infinity. And what I've done here is say that, well, if the first derivative is 0 in these places, then the first derivative acts similarly in each of these chunks. So for example, say I choose something over here. Let me get a color. So say I take negative 4 over here. If I know that the first derivative is negative for negative 4, then I know it's negative for literally everything here. Well, how do I know that? Essentially because if the first derivative is continuous, right, or even if it's not continuous, if I want it to go from negative to positive, it either has to hit a break, a discontinuity, which would be a critical number, right, or it has to go through 0, which would also be a critical number. But I know it doesn't do that except at this place and this place. So the first derivative behaves similarly in this chunk, and it behaves similarly in this chunk, and it behaves similarly in this chunk. So if I want to know if the first derivative is positive or negative, I just take a representative from each of these intervals and test them. So I'm going to take negative 4, 0, and 4 because I like my algebra to be simple. And then we'll just see what happens at these places, and that will tell us everything we need to know about the first derivative. So I'm going to take these intervals, or rather these representative chunks, and throw them into the first derivative and see what it spits out. And in particular, I don't care about the value over here. All I care about is whether the first derivative is positive or negative. Okay, so if you think about plugging in negative 4, right, that's going to give me 16 times 3 is, 48. So that's positive. If I plug in 0, that's going to give me negative 27. So negative, and positive 4, right, is going to give me back the same as negative 4, right, because this thing's symmetric. So it's positive on this interval, negative on this interval, positive on this interval. Okay, so then what does that tell me in terms of my critical numbers? So if I think about my critical numbers, I know that they were 3 and negative 3. So f of 3 is a local something, and f of negative 3 is a local something. Or it's also possible that it's neither a local min nor max. So in this case, you might want to pause again and try to interpret this through the lens of the first derivative test. So go ahead and pause if you'd like. Okay, so if I'm looking at f of 3, that's this chunk, right? Like 3 is living down here. Maybe I'll get my black pen back. So 3 lives in this chunk. It was negative on the left and positive on the right, right? So it was decreasing and then it started increasing, right? Which means that this y value must be a local minimum. Similarly here, right, negative 3 lives in this sort of change. It was increasing, and then it started decreasing, right? Increasing and then decreasing, which means that negative 3 must go with a local max. Okay, so the first derivatives test is leveraging up information about where the function is increasing versus decreasing to tell you whether it's creating the top of a hill, in which case you have a max, or whether it's creating the bottom of a valley, in which case you have a min. Okay, the next thing we want to ask is list the intervals where f is increasing versus decreasing. And we don't actually have to do any extra work to do this. We already did all that work. So again, you may want to pause the video and try and answer this for yourself. Where is the function increasing? So you may remember increasing means the first derivative is positive. Well, that's literally what we just figured out up here. So in this case, the first derivative is positive on the entire interval from negative infinity to negative 3, right? That's what this plus told us. And then either, a union symbol or a comma or whatever. But 3 to infinity was also positive, right? Which means increasing. And then similarly, like where it was negative, right? That's where the function is decreasing. In this case, negative 3 to 3. So that's a brief overview of the first derivative test and how it tells you about the shapes of graphs by leveraging information about increasing and decreasing. And remember, what the first derivative test does is tell you whether a critical number goes with a max or a min, right? That's the main takeaway.